All right, so we have one more installment of log properties here to look at in this video. And again, feel free to solve them and then fast forward to the end of the video and see how you did if you remember a lot of these from Hatu. Otherwise, I will explain each of them. And so this one gets to that property that I listed out. Let's go back up here, that you could do the same power to both things. So like, oh yeah, this second to last one here, that log base b to the n of a to the n is equal to log base b of n, or log base b of a. So you do the same power. And that power often comes as roots because roots are fractional powers. So like, for example, 36 and 25, I know those are both squares. So, so I could do the 1/2 power, right? This is 6 squared. This is 5 squared. So like, again, log base 6 squared of 5 squared. If I notice those are both squares, I can say that's log base 6 of just a 5. So in other words, 5 was the answer I would get there. Okay. So same thing here, log base 3 of 10 equals log base x of 0.1. Maybe you don't recognize it right away, but the thing is that 0.1 is the same thing as 1/10, which is 10 to the negative 1. And so if I think about, oh, well, I have log base 3 of 10 equals log base x of 10 to the negative 1. In other words, how did this 10 become 10 to the negative 1? Well, you did the negative 1 power, right? So if you raise the left side to the negative 1 power like that to get 10 to the negative 1, that means you can raise the base also to the negative 1 power as well. So that would be 3 to the negative 1 of 10 to the negative 1. And that's log base 3 to the negative 1 of 10 to the negative 1. So I should probably clean that up just a bit. So that would be like log base 3 to the negative 1 of 10 to the negative 1. And what is 3 to the negative 1? That's 1/3. So that would be the equivalency. Now here, right away, I'm noticing that the 8 and 27, like I'm hoping you see right away, those are perfect cubes. So I could cube root the 8 and the 27. That's the same thing as log base 2 of 3 equals log base 4 of x. And now I could say, oh, how do I get to 2 to 4? Well, I could square the 2, so now square the 3. So log base 2 squared of 3 squared. So x is equal to 9. Okay. Now, 0.2, that's 2/10, which is 1/5. So again, kind of same idea, log base 2 of 5 is equal to log base x of 1/5, which is just like this one, 5 to the negative 1. So I have log base x of 5 to the negative 1. So again, if I want that to be an equivalency to log base 2 of 5, we would have to do the negative 1 power here. So I do the negative 1 power there. So my x is equal to 2 to the negative 1 power, which is equal to 1/2. So again, you're not really, you're not really solving. You are, but you're really using that property. Now, look at this. So 625. So that's a power of 5. And so I'm actually going to look here, and 5, so 5 squared is 25. And then times 5 is 125, times 5 again is 625. So in other words, like log base 5, if I raise it to the 4th power, that'll give me 625. So then I should raise the quantity 4 root 2 to the 4th power. And so then if I do that, so I get 4 to the 4th power. And so I'm going to try to pick a different color here. Maybe go to red, show up. So 4 to the 4th power times root 2 to the 4th power. And root 2 to the 4th power, think about that's root 2 times root 2 times root 2 times root 2, or just normal 2 to the 4th power, which is 16. And 4 to the 4th power, that's 16 squared, or 256. So then we get 256 times 16. And again, that's a pretty ambitious number to do without a calculator, but it ends up being, I believe, 4,096 for x. So log base 625 of 4,096. But if I'm wrong, put it in the comments. Okay, and then last one here. So we're given log base 100 and then we're trying to figure out, well, what base is that? Would that get us all the way down to 2? And so for this, I want to think about what is 4 root 2. I know 4 is 2 squared, and I know root 2 is the 1/2 power. So I could think about it as 4 root 2. This is log base 100 of 4 root 2, which was 2 to the 2.5 power, or 2.5, which is the 5/2 power. So you might not think of 4 root 2 as a power, but it is. It's this. So now, how do I get this to just 2 to the 1st power? I'm going to do the reciprocal property, or the 2/5 power to both sides, or the both quantities. So that means if I do 2 to the 5/2, if I do that to the 2/5 power, that will give you a 2. So now I have to do 100 to the 2/5 power. And so, I'm okay if you want to leave it as 100 to the 2/5. If you remember, like what like the numerator versus the denominator of the 2/5, like what does what? Remember, the 5th is the index of your root, so it would be like the 5th root of 100 squared. So that's another way to think about that problem. Or you could leave it as 100 to the 2/5. Okay. Now, the last thing in this is that you have to be very careful. Last thing I say in this video is that when you are given a function, not a problem, notice that this was these are definite problems, like log base 36 is 25. That's a finite value, right? Here you have two functions. You've got log base 2 of just general x squared versus log base 2 of x times 2, right? So one of our log properties is that this 2 could come out in front, right? And simplify to this. And if it's an equation like this, you have to realize that when you do that, you change the domain of your function. Because when you leave it as x squared, everything in here will always say positive. And then, then even if you had negative x's, they still become positive before you graph their logs. So like, for example, you could make like a table of values, just see what that graph looks like. So x versus y. So we know 0 does not exist. So there's definitely a vertical asymptote at 0. And you try to put in 1. 1 squared is 1. So we get log base 2 of 1. So that would be 0. Because like 2 to the 0 would be 1. So I know it's here. But then if you put in negative 1 squared is also 1 before it becomes a logarithm. So you get its partner on the other side. And now if you pick, let's say, 2. Well, 2 squared is 4, so log base 2 of 4 would be 2. But notice that negative 2 squared is also 4. So both 2, 2, and negative 2, 2 have the same value. And then you could try maybe like 4 is the next power. It works. 4 squared is 16. Log base 2 of 16 is 4. Negative 4 would also give us the same. Well, that's kind of cool. 1, 2, 3, 4. 1, 2, 3, 4. Negative 4. 1, 2, 3, 4. Up 4. So it almost looks linear, but don't worry, it's not anymore. Because if I pick 8, so 8 squared is 64, log base 2 of 64 is actually 6. And negative 8 squared is 64, but then, again, log base 2 of 64 is 6. So if I go over 8, 3, 4, 5, 6, 7, 8, I'm only going up to 6 up here. And so it does eventually round out, but my point is that you get the characteristic sort of like log shape, but then you get its mirror image on the left because you were squaring things before you took the log. If you just have this, notice that your x will only be whatever it is you put in there. So the 2 would have come after the fact. So what ends up happening is that all of the negatives that we got here don't exist in this function on the right. So in essence, you've changed the domain. So you have to be careful. My point being that when it's a function like this, you cannot simplify this to be this and have the same graph. Because as soon as you start changing that, you're now changing the domain. But that's a contrast from number 5, because in number 5, you weren't graphing, like you were trying to evaluate this. So you could simplify things and pull squares out and get values. And that's okay, because you're not looking at it as an entire function. You're looking at it at one particular point. So, okay. So hopefully going through all 3 of those, just kind of refreshing yourself about things you learned last year in Hot 2 and reminding yourself about things we should know about in terms of logarithms for this class.